Now, get ready to level up your JavaScript game because our speaker, the one and only Nash, is about to take the stage.
My name is Phil Nash. I am a developer advocate at a company called Sonar. Sonar make things like SonarQube, SonarCloud, SonarLint, which are code quality tools. SonarLint lives in your IDE to help you stop writing bugs or security vulnerabilities as you're typing. And then SonarQube and SonarCloud sit in your DevOps pipelines to block any things that might go wrong at that point as well. If you've not given them a try, give it a try. SonarLint is for free. SonarQube has an open source edition. See what you can learn from them. They're really great. Again, my name is Phil Nash. You can find me if you ever want to ask questions or anything about this talk or anything else. Find me anywhere on the internet as Phil Nash, Twitter, Instagram, LinkedIn, or just my own URL, which, yeah, look at that. I'm just real pleased with it. Have been for years, sorry. Domain hacking, it's the best thing. Cool, let's talk a little bit about complexity. We're going to do this in 3 parts, starting with what is complexity. We have to sort of define the subject before we even get onto solving it, I guess. And so complexity, to me, is it's just everything, right? Our jobs are complex. We spend our time modeling real-life systems, sometimes not real-life systems, using a programming language that exists to help us tell other programmers what we're doing, whilst incidentally a computer managing to execute it as well. And doing that to model real life is actually kind of hard. Real life is hard. And therefore, code itself is inherently complex. And if we are working on complex problems, I have no issue in saying that some of our code can be complex for that. Complexity is inherent in the problem. But what I really want to avoid and help everyone here today deal with is the sort of accidental or extra complexity that we can add by perhaps leaving functions to run for 1,000 lines. I'm not going to show you any 1,000-line functions. The screens aren't big enough today. But that sort of accidental complexity that can creep into a system over time as we write it. That's the kind of stuff we're here to try and avoid and work with. And so ultimately, it turns out like our job actually is, aside from communicating this difference in, communicating with code, this real-life problem, is actually managing the complexity of that so that our projects don't come grinding to a halt, so that we don't find it impossible to change things because we cannot move a piece of a system without it all falling over. I gave a talk last year in which I dug into some of the data from SonarCloud, funnily enough, which scans hundreds of millions of lines of JavaScript, and picked out the top 5 issues from that, the most common issues at least. Now, some of them were a little trivial. It was almost disappointing to find that var being used instead of let or const was the #1 most common issue everywhere. And the other ones, commented out code. Like, don't do it, but it's not going to cause your program to fall over. It's just going to cause a light bit of confusion as you try and read that code. But I was delighted to see that actually there's a real problem in here, and that is what then inspired to write this full-length talk about it, is that the complexity of functions in JavaScript projects is too high. But that begs the question, what's too high? You see, if we decide that our code and our jobs and everything is complex, how do we measure that? How do we understand that? And so that brings me to part 2. How do we measure complexity? If I show you a piece of code and ask you how complex it is, how would you answer that? 4, exactly. That was call for 6 over there, I think. It's wrong, it's 8, and I will tell you why in a minute. Just to explain this piece of code, though, to start with, it's not important really what it does, but it's nice to sort of understand. We are summing prime numbers up to a number that you pass into the function. So we loop through all the numbers underneath it, and then whilst we're in that, we loop through all the numbers underneath that number, and if it divides one by the other, it's not prime, and so we move on. Otherwise, we add it up. How complex is this piece of code? I'm also taking guesses on numbers now, if you're going to shout them out. Well, I think it's 1. But again, I'll explain that later. Some other people would say 5. We'll see. This is a much simpler function, in my opinion. This is get words. If you pass a number in, it comes back with one, or a couple, or a few, or many, or lots. This function does not work for numbers less than one. I only realized that after I wrote the presentation. But again, it's not important what it does. It's important to see whether we think it's complex or otherwise. I think less so. You might have heard of this measure. Sorry, I will ask. Has anybody heard the measure cyclomatic complexity? Quite a few people. Some people haven't. Cyclomatic complexity has been around for a long time, I think since 1976. It is a way to measure the complexity of a function. Hooray. It measures that by providing a number, a score for a function, that's based on how many sort of breaks, loops, and conditionals there are in that. Indeed, actually, it starts by every function scores 1 for being a function in the first place. And so if you were counting the cyclomatic complexity of this, then yes, for being a function, this gets 1. Then for this loop, we add another 1. For this loop, we add another 1. For this conditional, we add 1. And this conditional, we add 1. And we get 5, which nobody said, not even me, because I still don't think that's exactly right. Because if we think this is 5, it turns out that this one is also 5. Get words scores 1 for being a function, and then 1 for each of the cases in the switch statement, according to cyclomatic complexity. And I think the idea that those two functions have a similar or the same level of complexity is not exactly right. It turns out really that cyclomatic complexity will measure the number of paths, number of ways through a function. And that's why it scores 1 for being a function itself. There's always one path through a function. If you've only written linear code, then it's going to go through once. And this is a useful score. This tells you how many tests you need to write to fully cover this function. Both of those functions would need 5 tests to be written to cover every kind of eventuality. But can we do better than that? If those two functions score the same under cyclomatic complexity, how helpful is that for us to understand how complex it is in terms of understandability, of actually working with the code and maintaining it? How do we measure that understandability? Has anybody heard of cognitive complexity? Fewer people. Good, that's why we have this talk. Excellent. Cognitive complexity is a measure that some fine people at Sona came up with in 2016. I can't take any credit for it. I've only been working there just over a year. And so back in 2016, we were having this problem with cyclomatic complexity as this measure of complexity. And we're like, how do we measure this understandability of it? Cognitive complexity measures things differently. It measures, it still gives you a score, but it creates it in a different way. It creates a score by incrementing, like cyclomatic complexity does for a break in flow, a loop or a conditional, but also by keeping a number in the back of its mind and using that to help the incrementation, this nesting score. So each time you nest inside of a conditional or a loop, we're going to add the nesting score, add 1 to the nesting score as well. And then when we hit another conditional loop, we add together 1 plus the nesting score. And this gives us, I think, a better understanding of that understandability of the code. If we take our examples again, we now no longer have to score 1 for being a function. That's out the door, that's fine. This is no longer about number of paths through that function. And yes, a function with an entirely linear flow will be 0 in complexity. And I like that, I feel that's reasonable, because we can just read straight through it. But this sum of primes now scores 1 for our first conditional loop, 1 for our first loop. And that increments the nesting score to 1. So when we get to the second loop, the second for loop in there, that scores 2. It scores 1 plus the current nesting score. And then it increments the nesting score. We get to the conditional on the inside, and that's now going to score 3 for being 1 plus being nested twice. Now, the conditional will then nest again, and so the nesting score will go up and then come down again without scoring anything. And eventually, we actually drop out of the second loop, we drop out of the inner loop, and we get to the conditional, which then scores 2 again. And that's why this is 8. Cognitive complexity of the sum of prime numbers here is 8. Higher than cyclomatic complexity, and higher than get words, which scores 1 for being a big switch. And I think this is reasonable, because a switch is based on a value that we only have to look at once and compare a bunch of times. If you rewrote this as a bunch of different conditionals, then that would score 1 for each of the ifs that you use, because each time you do a new if statement, you could be looking at a different value. You might not be, but you could be. And so that adds to the complexity. That adds to the things we have to keep in our mind as we read through this code. And I kind of see this makes sense to me because it feels like we're kind of adding things to a brain stack as we're kind of trying to think about how this code works and how we are trying to understand it. We just kind of keep adding things on the stack that we have to consider as we read the next line of code. And so when you're at the top of a function, you don't have anything to worry about. You don't know anything yet. But as you start to loop, we get inside the loop. We get inside another loop. Our stack kind of starts to build up. And over time, that is going to get, as the stack gets even higher, it gets harder to keep all that context in your mind. And then, of course, if you thrash about a bit, if you actually go up and down the loop a couple of times and then add things back onto it, that's also kind of difficult to keep that context in your head, difficult to keep all the things that are currently in context right there. And so eventually you drop out, things become calmer again, but at that point it's done its damage and we've scored 8, 12, 120, however long your function gets, or however deeply nested it goes. And so now if we understand that we have a complex job and we know how to measure it, then the next stage becomes conquering it and beating it. And that's the bit I'm mostly excited about, because this is the bit where we get to reduce that complexity and generally make our jobs easier over time. So the first stage in conquering this complexity is to understand where it is. And to do that, we know how to score it, but we need ways to see that score somehow. And so I believe, I have a tiny function here. It's not tiny. It's a function that does a silly thing, though. This is a function that works in my slide deck's in Reveal.js, and this function throws confetti onto a slide if I add confetti to a data attribute in some of the HTML. It's fun. But it turns out, I promise you, it is. It turns out this function is also quite long. It's got a bunch of, it is quite long. That's just, there's a big bunch of settings there. It's about 90 lines long. A lot of it's settings. But it's got a bunch of loops. It's got a bunch of conditionals. It's got a bunch of ternaries. I'll get to those later. In VS Code here, although available in other IDs as well, I have Sonalint. And Sonalint will measure my cognitive complexity as I'm writing it. And so we have a little yellow underline here to warn me that this has a complexity of 19. And the threshold is 15. The threshold allowed is 15. So that's what I say when it comes to that number 2 top most common issue in JavaScript, is that we find functions that have a cognitive complexity of more than 15. 15 is lightly arbitrary. It's actually quite difficult if you're writing small, compact functions to hit 15, which is a nice thing. But when you do hit it, I absolutely believe that is a time to consider what to do with that function, because something has gone wrong to allow the complexity to get that high in my mind. What this also does inside Sonalint is if you hit the quick fix thing and then hit show all locations for this issue, it tells you where all the kind of additions to complexity are occurring in this script, in this function. And so I have this big if that's around the outside. To start with, that gets +1, but that means that any of these conditionals on the inside, these ternaries, that's +2 because it's 1 plus the nesting score. That's a conditional, and then we get this nested ternary inside a conditional, which is scoring 3, and we drop in and out of things. That's 2, that's going to be 2. It's just 1 because it's an else if, I think. There are some extra rules to the cognitive complexity, and I will share a link to the paper that actually describes the whole thing later, which I do recommend you read. It's very interesting. And yeah, we get some loop down the bottom there. There's a load of complexity here. And so what we need to do is reduce that somehow. I'm not going to do that with this piece of code, though. I'm just going to carry on with the slides. It's 90 lines. You don't want to see me refactor that live on stage. That's a terrible idea. I have one prepared earlier. It's much nicer. Anyway, not the point. Come back to that. Second stage is to do nothing. Now we know we have complexity, and so that's using Sonar inside the editor. You could also use some kind of scan, SonarQube, SonarCloud, something else running in your pipeline that works out cognitive complexity for functions, and that can tell you about that in your code base as maybe part of your CI/CD pipeline as well. It's nice to know. So stage 2 of conquering this is not to do anything, which, as an also lazy developer, that's great. I love not doing things. If you were to discover that you had 100 lines, 100 functions in your project, or 1,000 functions in your product, and they're all of 100 in cognitive complexity, if you decided to drop all your work and set about refactoring all of them, what you've done is managed to achieve 0 in terms of deliverables for quite a long time, and put all of those functions at risk, because changing them is a risk. You could break something. And changing something when you don't need to, if you have no reason to change it, then there is absolutely no point in doing so. The risk is higher than the reward. So if you don't have anything to do with that function, do nothing. But yes, so complexity is only an issue if you actually need to change the code. If it's currently working and you don't need to change it, let it carry on. And then third, the idea is what we like to call clean as you code. In this case, this is where we come to refactoring. This is where you actually have to change a piece of code. You find out you're changing a piece of code in a function that has a cognitive complexity that is higher than you'd like it to be. This is the time to refactor. This is the time to change and reduce that complexity. In fact, if we refactor first, we can reduce the complexity of the code before we have to make the actual change we're going to make. It's going to make making that change easier. If there's a bug to fix or if there's a feature to add, it's going to be easier if we have reduced the complexity first. And actually, as part of the process of refactoring, you're probably going to understand the code even better, which is exciting. And so I say refactor first. And of course, importantly, refactoring is improving how the code works without changing what the code does. And that counts even if I'll get to that in a minute. That counts even if the code is currently wrong. And we'll come back to that. But to start with, how do we know we didn't change the result? I hope you're thinking tests. Good. Tests are really important here, right? If we're refactoring code, we're trying to change how it does something and not what it does. It's important for me to get those the right way around. We're trying to change how the thing does it, not what it does. And we need to know that what it does hasn't changed. And so those tests must also ensure that they test what a function does and not how it does it. And I have definitely failed this in writing tests in the past before. If you are reaching into the internals of a function in order to test its externals, then when you change those internals, that test will break even if the code itself is still correct. And so if you have tests like that, it's time to rewrite those as well. So if you don't have any tests for this piece of code that you need to refactor, that's kind of step 1. Step 0, you have to take a step back. We'll start again. And then it is important that, yes, those tests cover the existing behavior, what the function currently does. And actually, Aaron did a great talk on a very similar thing here last year? No. Oh, maybe? A similar talk on this using React components as an example of that, which I highly recommend watching as well. The important thing is that tests must cover the existing behavior, even if it's wrong. Because we are not changing what it does yet. We are just refactoring. It's so important to separate those two steps. And so then, yes, it is time to refactor. We have tests, and we are ready to change things. How are we going to now reduce this complexity? I think that's kind of this is, I guess, the crux of this whole thing. We need to understand where that complexity is, and then know how to change it. And so cognitive complexity as a score clearly has an issue with nesting. the way it keeps ratcheting up that nesting score in the background, tells me that it doesn't want you to nest things. And I agree. That kind of model of a stack on which I keep adding bits of context in my head absolutely works for me. And if I can reduce the layer of that stack, all layers, or reduce bits of it anywhere else, then I'll be much happier. And hopefully everybody else working on the code will be too. And so these are a few techniques that you might want to use to reduce that nesting and reduce the complexity overall. So that's inverting conditions and exiting early, structural collapse, extracting helper methods, and there are some other language features too. Inverting conditions and early exit is fun. So this is just kind of like snippets of that function I showed earlier. And in this case, as I said, I've got this big conditional that goes around the outside. This big one that says, hey, if there's confetti in the data set, then we can do stuff. And if not, go all the way to the end and see if there's an else, maybe. There isn't. But you don't know that at the top of the file, and it's 90 lines long. And so inverting the condition, that is changing this from if confetti is in it to if there's not confetti in it, and just getting out of that early. Oh, see confetti. Always surprises me. Yeah, checking if there's not confetti and then just exiting means that we can stop worrying about that and then just carry on. We don't have to be concerned as to whether there's an else. We can just, that's a simple thing that we can think of and then throw away and never have to think about it again. And then we can get on with the actual work of throwing confetti onto the slide. Nice and easy one. We just get to pop that kind of off the brain stack. We've got one less layer of nesting for the entire function. I like that. Step two, tip two, is structural collapse. This is not exactly in the original code, but I had to come up with something. In this case, we have the big if around the outside that says if there's confetti in the data set, then we'll do something else. And then it checks, in this case, if the media query allows for animation on the page. Prefers reduced motion. No preference means we haven't said, I want reduced motion, so we can have as much confetti as we like. And so we have these two consecutive ifs that both act on the same thing, and then we drop out the bottom of them at the same time. This only needs to be one conditional. We only need to nest this once. If we push them all into the one conditional, we only have to think about this condition the one time. We don't have to be worried about whether there's going to be some other effects outside of the internal conditional. And we can just simply, again, push them together and carry on with the work in the middle. And then obviously in this particular case, if it's both of those things, we can actually then invert that condition and exit early as well, and not even worry about it at all. So we can do structural collapse followed by inverting and exiting early, and I like that. So we just pop that off the brain stack. There's one less level of nesting, and I like that. Next up is extracting a helper method. Now, as part of that code, there's a bunch of ternaries that look a bit like this. And indeed, these ternaries do exactly the same thing, just with different arguments. And that tells me that we can absolutely extract it, because duplication is certainly not helping us. But there are other places to do that as well. Like, duplication is not necessarily the only reason to extract a helper method, but it's an absolute ripe opportunity for doing so. In this particular case, what we're doing is reaching into a different data attribute on the HTML, grabbing what should be a number in there, parsing it as an integer, and if there isn't a number in there, returning a default number. And so if we just extract that as a helper method, what we get is a bunch of things here, which I think is great. We get a well-named, I think that's well-named. We can debate that. Naming these functions is very important. We get a well-named function that says this is an integer data attribute or a default. And then when we call that in the code, when we call that in the main function, we don't have to worry about what the implementation of that is, whether it's this bunch of ternaries or whatever. We just know that we're going to get out of the other side an integer. Well, we'll get an integer either from the data attribute or the default. And so we've reduced, we reduce the nesting and the amount of ternaries and the duplication in the main function. But then inside of our helper method, we've also reduced the context that we have to consider when we then look at this helper method itself. Inside this method, we only care about an element, an attribute, and a default. And so if it turns out that this is where a bug is in our code, we don't have to deal with the context of the entire function. We're just dealing with the context within the helper function. I thought there was going to be another thing on that slide. So reducing the context is important. If you write a helper method that it turns out uses all of the context from the existing function, you're not helping anything there. You're actually just moving the complexity around and actually moving it off into a different place, which is going to make it more complex ultimately. Although it probably will still reduce the score. It's not perfect, but what is? If you don't reduce that context, then yeah, you still have everything to keep inside your head whilst you're inside the body of that kind of helper method. And so extracting helper methods are great to reduce duplication, but also to reduce context within themselves. Make sure that they're not complex on their own. And just pop it off the brain stack. Duplication in slides is fine. And finally, there are some JavaScript features which help us out here as well. This is just a couple, but if you have nested objects, the old way of finding out whether you could safely get to the end of a set of multiply nested things was to check that the first one exists, and then check that the internal one exists, and then check again. And that's it's a pain, isn't it? It's much easier to read optional chaining, which is still a relatively new feature, I guess, in JavaScript, but much nicer to read. If we use that optional chaining, then it's understandable and concise, and I like that. And secondly, I kind of had to make this example up as well, but if we're checking that something is either undefined or null, and then assigning if it is either of those things, we can do that with the... I knew I should have written this on the slide. The question mark equals nullish coalescing operator, I believe. And this just says everything that we said here, which is if this is undefined or it's null, then we can assign it. And we're happy about that. So we move it into one line, we reduce the nesting, we actually lose a conditional entirely, which is lovely, and it's much more understandable again. So that's nice. And we just get to pop some of those things off the brain stack. I think we've got time. Plenty of time. For a tiny bonus rant. You see, I've written a bunch of ternaries in that example code. I'm okay with ternary operators. They're fine. They're useful for a single line, quick check of a conditional. They are concise. They're useful. They're expressions. They return one or the other result, unlike an if statement. But, and I know this has mostly been about nesting in this part of the talk, who's into nesting ternaries? Some people. All right. That's okay. You're allowed to be wrong. Nested ternaries can all go disappear into the sea. There was a resurgence in talk about nested ternaries recently. At the end of last year, Prettier, the formatter, released an experimental format for nested ternaries, and this was their example code for that. I don't think you should be experimenting with nested ternaries. That's barely the point, though. The point with this kind of formatting of it is that, if it's a long thing, it ends up on several lines, and if it's a short thing like that one, it ends up on one line, and Pretty will make it up for you. It doesn't matter. But I really dislike reading this. I do not find it very understandable, and it is simply because of the nesting, in fact. And I know in my head, in order to read something like this, I'm absolutely substituting the question marks and the colons for ifs and elses, and I'm trying to place brackets on the page instead of me. And so this says, if the pet can bark, then if the pet is also scary, then it's a wolf, otherwise it's a dog, otherwise if it can meow, then it's a cat, otherwise it's probably a bunny. And I only know how to do that because I've given this talk before, and written a whole blog post about it. I disagree with this in a bunch of ways. Firstly, we've got the nesting, but secondly, it's just a bunch of symbols that I actually find genuinely hard to read. And that might be personal, and everybody else might be fine with that, but I doubt that's the case. And really, when we are writing code, we are not just considering what that code does right now. We're not considering what it does tomorrow. We have to consider how we're going to read it the next day, or in 6, 12 months' time, or how a colleague is going to read it, or how a junior developer is going to read it, or how a very angry senior developer is going to read it. We have to consider actually how other people are going to interact with this code. Secondly, I actually think we can improve this in a bunch of ways. We could be testing it. We could be extracting it to its own function. We could be using kind of early returns as a way to escape these kind of nested ternaries. And I'd rather see it like this, in which it's actually a lot easier to read, because I can say if a pet can bark and the pet's scary, then it's a wolf. I don't know who is keeping wolves as pets on the Prettier team who wrote this. Although I wrote this bit, but wrote the original one. Then if it can bark, at that point it's a dog, and if it can meow, it's a cat, otherwise it's probably a bunny. Not only, I think, is this more readable, sure, it's more characters, but I'm not worried about characters. I don't have a memory limit on my computer for the number of characters I can put into a function. I have a big memory limit. But it allows us to test this independently as well, and we can be sure and certain of what's going on inside this code. In both an automated, a testing way, as well as a little bit more sure when we actually read it out loud to ourselves. And so, I don't like nested ternaries, and I hope you can all stop doing that. It's not just for me, I promise. Every time you are nesting, you are increasing that score, and if you're nesting inside a ternary, you're just making it even harder to deal with, I think. And so that's what we looked at. We've checked in on what is complexity. I absolutely think that we have hard, complex jobs. That's why we have to spend days listening to other people talk about them. And some of the experiences that I've heard today have just been great. But understanding that complexity is important in order to make sure that we survive into the future and keep on working. We've looked at how we measure complexity. I really like cognitive complexity as a measure for this. Like I said, it was invented, 8 years ago now. 9 years, I think, actually. 9 years ago now. It's been around for a little bit, but I really think it's a useful measure of that understandability and maintainability, and I absolutely recommend that you find a way to kind of apply that to your code and see where the problem areas might be in terms of complexity, because those are the ones that are going to slow you down eventually. And then we looked a bit into this conquering complexity and how to refactor. And of course, once we have done that refactor, as I was saying earlier, we do need to, once you've done the refactor, you can commit to that, you can be happy with that, and then go on to make the change that you had to make in the first place in order to, and it should be easier to make that change, and it will be easier in the long run to change your code. And if you continue to clean as you code, if you continue to refactor functions and reduce the complexity over time, then as you work on your code base, as you change that code base, the whole thing is going to get easier to use over time, which I believe is normally the opposite of how legacy software manifests itself. And so maybe if we conquer this complexity as a team, as an industry, then we'll never write legacy again, and all we have to do is deal with things complaining about dependencies being updated. But we can't do anything about that. We'll keep our own code base clean, and we'll handle the complexity of everybody else's code base in another way. As I said, I will share out the slides, link to these slides, but if you are looking for tools to help you out with this, of course, as I said, Sonar Cloud, Sonar Cube will scan your code, and for many, many potential issues, but I think importantly for this cognitive complexity one, SonarLint will do so in your IDE on the things you're working on right now, allowing you to address that as you're working on it. If you are already using ESLint, which is also a perfectly reasonable way to scan your code, ESLint does not have a score for cognitive complexity within it, but the Sonar JavaScript team produced an ESLint plugin, ESLint plugin Sonar.js, which includes cognitive complexity as well as a bunch of other rules that are not part of the regular ESLint rules that we also think are good and useful. But if cognitive complexity is all you want, you can just switch that one on, of course. And so I'd recommend that. And then, as I said, I absolutely recommend reading the cognitive complexity paper. It's not a very long read. It is a lot about Java rather than JavaScript, but the patterns and most of the patterns and things hold up the same. And it's really useful to understand some of the more, there's a few more intricacies which I didn't go into depth with here. There's my blog post on nesting ternaries, read it. Exactly. Yes, I do have a passion enough to write a blog post about it and post it on the internet and then take the wave of comments on Reddit. And then if you want to throw confetti onto your slides, the plugin is also open source, so feel free to use that. And sometimes it looks like this. So, thanks very much again. My name is Nash. I'm a developer advocate at Sona. It's an absolute pleasure to talk to you today and to be part of this conference. And I think we've got a bit of time for questions, but otherwise, thank you so much.